In this lesson, we're going to finish up our study of polynomials by talking about modeling. We're going to talk about writing polynomial functions or models. Really, that means the same thing. We're going to take a set of information and we're going to write an equation for it. First thing we're going to talk about is doing it from a list of zeros. So we'll do that for our first example. Basically, we use the information we know about how polynomials work as far as their factors and their zeros in order to construct the equation. Then we're gonna learn how to do it from a set of just numbers, not just the zeros. There's some tricks for determining the degree that we can use, although technically the process we're going to use scales, so arbitrarily big degrees work pretty much the same way. When you get to actually writing the equation, I put it as two separate points, but really these are 2 and 3 here are basically the same procedure as part of writing the equation. Determine the degree. If you can determine a precise degree, which means you have precise points on a graph, you can find the coefficients for that equation using matrices, which is what we'll be doing in our middle two examples. And then we're going to end up with a cubic regression problem, where I'm going to show you how to do cubic regression. I'm actually going to do it twice, once on a TI-84 graphing calculator, and once on the online tool we use here called Desmos. There are other tools that'll do cubic regression, but these are the two my students use, so those are the ones I'm going to show. So first of all, from a list of zeros. So I need to write a polynomial function that goes through these points. Now this looks like a list of zeros, and there are zeros on the list. But if you are paying careful attention, you'll note that this is not an x-intercept. This is a y-intercept, so it's actually not a zero of my polynomial. It's the y-intercept. I'm going to use it at the very end to determine the leading coefficient of my polynomial, but what I need to do first is find the factors for my polynomial. Since there are 3 zeros, and I'm assuming I have the entire list, I'm assuming this is a third degree polynomial that I need to write. So I'm going to write it. I'm going to create one factor. Oh, I'll put the leading coefficient out front. I'm going to create one factor for each zero. So my first zero is -2, which means the factor that goes with that is x plus 2. X minus -2 is x plus 2. Then there's a factor for my -1, 0. That'd be x plus 1. And then 1 for my +1, 0. That's x minus 1. That pretty much everything about this polynomial I know now, although I need a leading coefficient, which will eventually get distributed. So it's actually quite important as far as the polynomial is concerned. And that's why I need a point that's not a 0. If you don't have any points that aren't zeros, then a could be anything and still go through these 3 zeros. So if your instructions include finding a specific polynomial, they have to give you an additional point. If they just say write a polynomial that goes through these zeros, then you're free to satisfy those conditions while making a be anything you like, including 1, which is definitely the easiest. So in order to figure out what a should be, I take this point and I stick it in. 6 is the answer when x is 0. So that winds up being 2 times 1 times -1, which is -2. So -2 times a is 6, which if we divide -2 on both sides, we find out that a is -3. So my actual polynomial here is -3 times x plus 2 times x plus 1 times x minus 1. Now if the instructions say in standard form, you got to multiply all this out, which you should already know how to do. But if you don't, you can check my other lessons from chapter 5. Multiplying polynomials, that was 5.4, I think. I suppose I'll look. 5.4, yes, indeed. All right. So but I'm going to stop here because multiplying polynomials out is not what this lesson is about. In my second example, I have a table of values. These are not zeros. These are just points on my graph. Now, for finite differences and using matrices, You have to be careful to check your assumptions. This assumes that you need a polynomial that goes exactly through each one of these points, which is not normally how you encounter data that's been collected from the real world. Usually we consider the points to be approximations, and you're going to approach it as I just need to get close, and that's where cubic regression comes in. But for this lesson, we're talking about finite differences, and that requires us to assume that our numbers are precise. So the graph actually goes through all of these points. In order to figure out the degree, the minimum degree I can use in order to write an equation that mirrors this relationship, I'm going to use a process called finite differences. What that means is you take your y's. I like to write them leaving a space because I'm going to write numbers sort of underneath and in between them. But the actual spacing is just helpful. It's not required. Now, the way finite differences work is you're going to figure out how much y changes between each of its y values. You can do this by taking the second one and subtracting the first one. 15 minus 6 is 9. Although I find I do that as a backup. The way I find is fastest first is to ask myself, how far do I have to go to get from 15 to 22? Which is a synonymous question, but I find usually my brain responds to that faster. From 15 to 22, that's 7. Whereas I could subtract and I would come up with the same answer. Just make sure you subtract because in a situation where you're going down, you want to make sure your answer is negative. So make sure you subtract the one on the right minus the one on the left. So 21 minus 22 is negative 1. Don't do that backwards, or you'll have the wrong sign. To get from 21 to 6, I have to go down 15. And to get from 6 to 29, I have to go, to negative 29. That's negative 35. So these are called the first order differences. First order differences. And the only thing that's significant about them is if they were all the same, then the relationship would be first degree or linear. These are not all the same. So what I'm going to do is find the second order differences. Or take the difference again. So to get from 9 to 7, I go down to 7 and negative 1, that's down 8. Negative 1 and negative 15 is down 14. And negative 15 to negative 35 is down 20. These are also not the same. If these were all the same, I would expect a second degree relationship or quadratic. I'm going to repeat this process again, finding the third order differences to be negative 6, and negative 6, which is excellent because these are all the same. So if you get to a set of finite differences where the bottom row is where the differences are all the same, then you found the degree of your relationship. This is a third degree, third order, or third degree relationship. So the correct standard form for my equation is going to be ax cubed and bx squared and cx and d. We haven't yet done a situation where we need to produce a cubic model using a list of points, but we did it with quadratics. And what we found was if we had when we had second degree, we had 3 letters, ax squared plus bx plus c, so we needed 3 points. Since this is third degree, we have 4 letters, and we need 4 points. I'm going to use the first 4 points. It doesn't actually matter. It's just I'm going to need to cube these numbers, so if I stick with the ones with smaller x's, it makes life a little easier for me. So I'm going to take each of these first 4 points, and I'm going to apply them into this model, where I stick for like 1, 6, I'm going to stick the 1 into all the x's, 6 is the answer, and that's going to produce for me a system of equations. If I stick all 4 points in, I'll have 4 equations with a, b, c, and d being my 4 unknowns. It's a system of equations I can solve. I'm going to use a matrix to solve them quickly rather than trying to do it by hand, which for a 4x4 system would take a while. So my first equation then is 6 equals 1 cubed is just 1, so this is just a. 1 squared is 1, so that's just b. That's just c. D is always by itself. So when I stick in 2 for x, I'll get 15. Now 2 cubed is 8. 2 squared is 4. And this is 2c. D is always just by itself. So I'll get 22 if I do 3 for x. 3 cubed is 27. 3 squared is 9. 3c plus d. And lastly, 21 would be 4 cubed is 64. 4 squared is 16. 4 and d. So here is my system of equations. I'm going to distill from this a 4 by 4 coefficient matrix and a 4 by 1 constant matrix. I'm going to do the inverse of the coefficient matrix times the constant matrix, which is going to give me my values for A and B and C and D. So let me drop this down so you can see. All right, I was using the graphing calculator last, so I am going to back up and use a matrix calculator. So this is Desmos, desmos.com, and I can create a couple matrices. Down here I adjust the size. A needs to be a 4 by 4 matrix, and my second one wants to be a 4 by 1 matrix. The coefficients, I'm looking at my paper still, are 1, 1, 1, 1, 8, 4, 2, 1, 27, 9, 3, 1, and 64, 16, 4, 1. Then my constants were 6, 15, 22, and 21. You can hop back and check them if you think I was wrong. And as I said, I need the inverse of the coefficient matrix times the constant matrix, which gives me negative 1 for A. So it's negative 1x cubed. 5 for B, so that's 5x squared. And C is just 1, as is D. All right. So I'm going to drop this back down. As you can see, so I've got negative 1, 5, 1, 1 as my coefficients, negative x cubed plus 5x squared plus x plus 1. That is my polynomial that goes through all of these points. I know it goes through the first 4 for sure because I solved the system of equations. I know it goes through the other 2 because my finite differences tells me this is a third order relationship. All right, I'm going to do that again. I'm going to talk less and go faster so that you can see what I'm doing again. Hopefully the second time will help you some. All right, from 1 to 5 is up 4. From 5 to 12 is up 7. From 12 to 22 is up 10. And from 22 to 35 is up 13. These aren't all the same. From 4 to 7 is 3. 7 to 10 is 3. And from 10 to 13 is 3. That's only the second order differences. So this is a quadratic relationship. F of x equals ax squared plus bx plus c. So I only need to take the first 3 points. So 1 equals 1 squared is 1. 1 and c is by itself. If x is 2, this becomes 2 squared and 2 c is by itself. And for 3, I get 9 and 3b and regular old c. So I need to go up to A here and reduce it to a 3 by 3 matrix. B will be a 3 by 1 matrix. Let's see, my top is still 1, 1, 1, but my bottom is 4, 2, 1. Sorry, middle. And my bottom is 9, 3, 1. And the constants are 1 and 5 and 12. So for A, oh, interesting, fractions. Did I mess that up? Five, 12. Oh, no, it's fine. Okay, so that's 1.5 x squared minus 0.5 x. Oh, and nothing. So there's my polynomial of second degree. For my last example here, I am using regression, which means I don't expect my polynomial to actually go through all of these points. I'm going to get it as close as I can. So I'm going to start with Desmos. Since we're remote this year, most of my students are using Desmos. I'm going to bring it to the top. But I need to go back and use the graphing calculator for this. So the way to do regression using Desmos, go up to this plus here. You need to first produce a table. It doesn't really matter what the variables are called, although x1 and y1 works as well as anything. The table, 1, 5, 2, 13, 3, 17, 4, 11, 5, 11, and 6, 56 is like so. Can't really see it all, but there is a zoom button over here, which just lets you zoom this. Actually, let me grab that. Oh, this window's not the right size. Okay. Oh, I just moved the wrong thing. Oh, man. It's going to cause problems later. All right. I should have left well enough alone. So here's my scatter plot. I can see it. It looks like it turns here and then it turns again. 2 turns is consistent with cubic. Although this year you won't need to determine the correct degree for your regression. That's something we do in pre-calculus. In Algebra 2, the instructions are going to say either use finite differences to determine the degree, or use cubic regression. So for cubic regression, then we're going to tell Desmos that we want an approximate answer. So we have to make sure we use the same variable up here in our y column, y1, and we use the tilde, which is usually underneath your escape above your tab. It's a little squiggly line. That's in this case it means approximate. And we're going to do basically what we wrote down on our paper. We're going to use letters as our coefficients. Now I'm doing cubic regression, so I'm going to call it ax cubed. I want bx. Oh wait, I can't just say x because my variable up there is called x1. Okay, the x plus c x1 plus d. So as you start typing it out, things will float up as it tries to help you. This here is my cubic model, and here it has a sketch of its graph. You'll note it does not go through all the points. It's the best fit we can make from a cubic model. Now, how good a fit this actually is, you can determine by looking at this correlation coefficient right here. Number close to +1 is good. Exactly 1 would be perfect. That's where it goes through all the points. So if I did this for one of the previous 2 examples, you'd see a correlation coefficient of 1 because it goes exactly through every single point. As is, it doesn't go through every single point, but this is still a pretty good fit. Those residuals are pretty small. This is almost 1, and 1 would be perfect. So these are my coefficients. It's 2.7 x cubed, negative 25.5 x squared, 71.8 x, and negative 45.7. So this is cubic regression. That's how we do it. Just to illustrate my point, since I'm here anyway, I'm going to go through and put in the previous problem, 1 and 5 and 12 and 22 and 35, and this was not there. Okay, so you'll note I told it I wanted a cubic problem. Yes, well, that's weird. The formatting here is kind of weird. and it returned for me an r squared of 1. So it says this graph goes exactly through all of these. Although you'll notice this right here is something that we've seen in our calculators before. That number more rightly should be 0. 2.9926 times 10 to the negative 16, that's 0.0000, like 15 zeros. And then and the same thing down here. These numbers are 0, it's just the calculator is trying to be precise, so it doesn't round appropriately. So a should be 0, which is what makes this not cubic, because if a is 0, this term shouldn't be there. B is the first one that has an actual non-zero value, so this is a quadratic relationship once you get it all typed in. And you'll notice, like we discovered when we did it earlier, the number on the end should be 0. So it's 1.5x squared minus 0.5x, what we experienced last time. But the r squared equals 1 clues you into the fact that this is actually a perfect fit, not just approximate. I'm now going to switch out of this to the bottom, but I messed up my other window, so now I gotta fix that. Okay. So this is Texas Instruments TI-84 calculator. It's the one that we used in class back when we used to come to class every day. So I'm going to type this table in to my graphing calculator. The way we type in a set of points for statistics is in the stat button right here. Stat. Go to stat and choose edit. You should have an L1 and an L2 column. If you want to clear those out, go up to the top, push the clear button. Don't push the delete button. It erases the title at the top as well, which you don't want. So L1 is going to be my x's, 1, 2, 3, 4, 5, and 6. L2 is going to be the y's, 5, 13, 17, 11, 11, and 56. Now if you want to produce a scatter plot, you go to y equals, turn on plot 1. You should make sure you turn off everything else. Just like we zoomed in Desmos, there is actually a zoom option for a scatter plot, which is zoom stat number 9. And that will automatically configure your window so you can see every single point on your scatter plot, which is nice, because if we went like negative 10 to 10 and negative 10 to 10, we wouldn't see all but one of these numbers. So if you want to see it, there it is. But you don't actually need to look at it on the TI-84 in order to do the regression. But go back to the stat menu and over to calc. Now you need to choose which type of regression you want. Although, like I said, this year I'm going to tell you. So cubic regression is where we're going. Make sure your X numbers are in the correct column and your Y. We did them in L1 and L2, so we're good to go. If you want it to graph, you got to store your regression equation into the Y equals menu, which you get to in the vars menu. Go over to Y variables, and we're in function mode, so we choose function Y1. So what this will do is once it finds the equation, it'll save it as Y1. We don't need to do that though. This right here, you'll know, are the same numbers we found from Desmos. 2.7 x cubed, negative 25.5 x squared, 71.8 x, and negative 45.7. We also got the same correlation coefficient here. Now because I saved it, it automatically put this whole thing, it doesn't round at all, so all the digits are there. You'd have to scroll to the side to see it all. And you can also view the graph to see what you think about the fit. It actually looks better on this window than it did on the first one, I think. But this is a fairly good model, and now we have a decimal approximate, a model for this data. This is more typical for data you encounter in real life. Stuff rarely works out exactly and precisely. So this should get you started. 5.9. Oh, and I guess next we'll be reviewing, but good luck on this assignment.